right? And B is going to be 33. And so if we trace out this code, it asks here, what is, I guess it does A times C, right? So 21 times 23. Everybody with me there? And so it asks, what's 21 times 23? And in order, when it recurses, now it needs a new block of memory to run the new iteration, the new call, right? So it allocates this new block of memory because all these variables need to have their own values. For example, x here is 21, while x here is 2,133, right? So now when we run this one, it does the same thing. The first thing it does is it multiplies A and C together, which is 2 times 2. So, right, so it's asking what's 2 times 2, and it calls what's 2 times 2, right? And what does it do now? It just says, hey, this is small, let's just do it. So it computes it itself, and when it gets the answer, it pops the stack, right? And it comes back up here and says, great, the answer is 4. All right, and now it's asking what's B times D, and that would be 33 times 12, if I'm not wrong. Oh, no, sorry, we're here. What's 1 times 3, right, which is 3. Right, and so that gets the answer here. And now then it does A plus B. A plus B is 3 plus 5. Right? So it says, what's 3 times 5? It's 15. It returns. Right? And then it does all this various math. It adds and it shifts, and it comes up with the answer is that. People following this? And now this guy is done, so what does it do? It pops and it puts the answer up here, right? And then we ask, what's B times D? And this is the one where it's 33 times 12, right? And then it asks, what's 3 times 1? And that's 3. And then it asks, what's 3 times 2? And that's 6. And then it asks, what's 6 times 3, right? And we go on forever. Everybody get lots of insight from that? Now, you should certainly know in your back of your mind somewhere that this is what's happening in the computer, right? But if ever anybody asks you, explain to me how this computer program runs, and you try to explain this, then bad things will happen. Certainly if you ever do it to me. Right? People, there's no way you could describe this in a paragraph during a test. Right? We don't want this. Everybody got good? All right, so stack of stack frames, right? Well, it shows you what actually happens in the computer. It's very concrete. People, actually I haven't gotten one of these in a few years because I am sufficiently threatening. But I certainly, for years, got people trying to trace out the program when I asked you to explain this program, and it was unreadable. Right? So it's unreadable, it doesn't explain why it works. We only did it for one input at best. Alright, so now, I don't know what happened to all my little red circles, but now we're going to look at the tree of stack frames. Tree of stack frames is in some ways the same thing that we did before, except we put all the stack frames out, right? Remember, this guy called this guy, who called this guy, who then called this guy, who called this guy, and then this guy called this guy. Right? And people remember the idea of depth first search? Right? We're going to be covering depth first search in this class, but basically it's the tree, and what happens is the computer does a depth first search of this. Right? So when you're running this, what's actually in the computer is this, this, and this. Right? Everybody with me here? So the pros of this is you can see the entire computation kind of laid out. Though what it's really good for is if you want to compute the running time. Right? That's kind of what we did when we were doing running time. Right? We laid out that tree and we counted how much work does each box do and how much work at each level and how many levels. And we added it all up. So it's good. That's what we do. We do this for running time, but we don't do it for much else, right? You certainly don't want to have to, in a paragraph, describe this tree, right? You have to think about what are all the boxes, stack frames going to happen, and who's calling who, and what is all their inputs, and it's too much, right? Everybody with me there? You know, the structure of the tree may be very complex, and we don't always know what's happening. All right, so now we're going to look at friend strong induction kind of view of it. All right, so just like when we were doing loop invariants, right? We said we're at the top of the loop the first time. We proved that when we come around, if the loop invariant is true at the first time, and it's true the second time. If it's true the second time, it's true the third time. But do we have to do that over and over again? No, we do it once, right? So we look at kind of typical guys. Let's look at a typical box, and it has a particular input, and we just worry about this one box, right? We don't worry about the entire computation because it's far too much for us to handle, right? We worry about this box. It has this input, it has these friends, it produces this output. We prove that if the friends do what they're supposed to do, we don't worry about the friends, but if they do what they're supposed to do, then this box will do what it's supposed to do, right? And once we do it for that box, right, and I guess then we, we do it kind of generically. How do we do it? We consider our input. I said this already, but let's say it again. We consider our particular input, right? And from our input, we construct some number of sub-instances, right? And we assume by magic that our friends give us the answers for those. And we use their answers to construct the answer to our instance, right? This is our instance. We ask our friends these questions. Our friends gives us the answer. From them we get an answer for our instance, right? So, and as I said, we don't worry about who our boss is. We don't worry about how our friends do their instance, right? We just worry about our one single box, right? This is, divide and conquer. Right, so we think about a generic instance, and there are two cases, right? There's the generic instance when we recurse, and there's the generic instance when we have the base case. And we make sure that for any input, if these work, then this works, and we prove that this works. Everybody good? Right, so don't worry about anything else. And now, since we prove that a generic one of these works, that kind of proves that all of these work. And we prove that a generic one of these works, that proves all of these work. And if they all work, assuming that they all work, then they all work. Right? Sort of a circular argument, but life's good. All right? So let's get to the topic of circular arguments. What are we doing when we're writing a recursive program is we assume that we already have an algorithm that solves the problem, and we use it to write an algorithm that solves the problem. Right? Seems like a circular argument. So for me, this happens to me sometimes. I'm locked out of my house, and my key's in the house. And I think, man, if I could only get in the house, I could get the key, and then I could lock the door and get me in the house. Right? Well, that's really, everybody laughs, but that's circular argument. So, how do we break that circular argument with recursive programs?
Bomb. Base case.
The base case. What else? What am I allowed to ask my friends?
Lend me your key.
Yes, actually.
Smaller instance.
Smaller instance. Yeah, so what's really happening is there's not one house, right? There's a sequence of houses, and they get smaller and smaller, right? So this is my house, and I'm trying to get into my house, and luckily the key to my house isn't locked in my house, right? Because then we really have a problem. Luckily my key is locked in my friend's house, and my friend's house is a little smaller. But the problem with my friend's house is it's locked as well, right? But his key is locked in his friend's house, which is a little smaller, and his key is locked in his friend's house, until we get a teeny little house that's so small that we can solve it on our own, right? So the key here is you can allocate work, you can ask your friends anything as long as they meet the following two requirements, and put these in your brain because they're very important, right? The one is it needs to be a smaller instance. Now, what's the definition of smaller? And I've had long assignments working on the issue of smaller, right? The definition of smaller isn't so well defined, right? And one of the problems when people are writing code and their code doesn't work is, we could say, hey, does this, could we use this? If we're using, maybe our input's a graph. So is size the number of nodes, or it's the, you can measure. Or maybe here's an example. Suppose that the input with the GCD algorithm, right, and I have two numbers, x and y, right? Is the size of the input the value x? Is it the value y? Is it the sum of x and y? Is it the product of x and y? Is it, the number of bits in them? Right? There are many definitions of size, right? Now, when we're doing running time, what's the definition of size? It's the number of bits to write it down, right? The number of digits to write it down. But when we're talking about the size of an input for a recursive program, I don't care what you use as the measure of your size. There's only one thing I care about. It's that you're consistent, and then it gets smaller, right? And the other key thing that's important is that you have to talk about your pre and post conditions, and what you ask your friend has to be an instance of the same problem that you're solving. It has to meet the preconditions. All right, so they get smaller. And the other thing about the size is if, according to your measure of size, the problem gets sufficiently small, then you solve it on your own. Right? Everybody good with that? All right, so that's the brute force. You solve it on your own. Just last term, I stuck these last slides in here, which kind of show a parallel between what we did in loop invariance and what we're doing now. All right? They're not completely the same, but they're very similar. All right? What's similar to loop invariance? Well, actually, it's the pre and post conditions are very similar to loop invariance. Right? All right, what is a pre condition? It states a statement which has to be true about your input. Right? Why is it so crucial? Now, when we were doing iterative algorithms, it's important to have a loop. It's important to have a precondition, right? Why? So you can establish the loop invariant. But now it's really important. Why is it more important to have a precondition than it was before?
Because you have the same problem.
Right, exactly. Not only do I have to worry about what instances, what problems do I have to be able to solve, I also have to know what am I allowed to give my friend. Right? So it's a double whammy there. Same with the post condition. Not only do I need to know what's expected of me, I need to know what I can expect from my friend. Right? And so, how is this related to maintaining the loop invariant? Maybe this might be a later slide, but as we recurse down, what are we maintaining? It's the precondition. Right? I have the preconditions true for my input, so it's true for my friend's input, so it's true for his friend's input. We're maintaining the precondition. And what do we maintain as we bubble back up? The postcondition, right? The postcondition was true for his instance, so it's true for my instance, right? All right, again, with the iterative algorithms, we worry about one step, we worry about one stack frame, right? You don't, it's like you're flying it from Mars. All you know is you're given this input and it meets the precondition. That's all you know, right? And what is your goal? Your goal is to get the solution for your instance, and you do it by help from your friends, All right. Don't, this is kind of what I said already. No global variables. Don't worry about who your boss is. From your instance, what's the step? I have the precondition is true. What's the step? Is I construct subinstances for my friends for which the precondition is true, right? And for which I've made progress because the instance has gotten smaller, right? Right? How do you stop this? It's the idea of if my instance meets my precondition, then my friends do, right? How do we make progress? The instance gets smaller, right? The size of your instance, and right, this is another requirement of size, is your instance can't be infinitely large to begin with according to your size, or that's kind of, right? And by smaller too, it really gets smaller so that it eventually gets small enough. Maintaining the loop invariant. Right, so this is the same idea as I said already. We're going to look at strong induction in a minute. Right? All the things I've said before. Right, so how do you get the postcondition? Well, if my friend's solution meets his postcondition, then my instance will meet my postcondition. Right? And another thing that happens is often I will give you, in the loop invariant type of algorithm, if I give you a pre and a post condition, don't change them. Right? That's the problem I want you to solve. But for recursion, often we'll see that you do have to change the pre and post conditions. Right? Because you want to get more, you have to give more to your friends, or you want to get back more from your friends. And so, if you're going to change your pre and post condition, this is very crucial. You have to document to me what you're doing. Right? Tell me what the pre and post conditions are. Make sure that your friends meet them. Make sure that you handle all the cases. Right? And if it gets sufficiently small, you solve it on your own. These are all right. Everybody kind of good with these things? All right. So how does
So we have to prove the initial case, the many cases, and then the final and smaller case, the three of them? Is that what you said, or just one enough? Like when you're going down cursively, you have to say something for the last case?
So, if you look at your code, and there are blocks in your code, you have to kind of handle every path through the code. In the example we just looked at, there were two. Your generic guy who recurses, and your generic base case.
Okay.
Often there's three, because I have a left friend and I have a right friend, and I handle them differently.
Okay.
Right? All right, so how are we doing induction? Well, let the statement S of I be the statement that my program works. Oh, first off, what is strong induction? Right? Regular induction is you have a statement for every integer. And in regular induction, you prove that the base case is true. And you prove for all I, if it's true for I, then the statement's true for I plus 1. Right? And then by induction, you get it's true for all positive integers. Right? For strong induction, it's actually easier to prove things by strong induction. Right? Because you don't actually even have to, you prove the base case, and then for every I, you assume that it's true for every I smaller than your I. And from that, you prove that it's true for your I. So the reason it's easier, here, you have to prove that it's true for I plus 1, and you only know that the immediate previous is true. Right? But now you have to prove the same basic thing, but you have that all previous are true. Right? So you have more at your disposal to help you prove things. Has everybody seen strong induction and kind of relate to it? Anybody want to talk about it? Why does this follow? Well, if I know 0's true, well, I know 0's true, so 1's true. Now I know 0 and 1's true, so 2's true. Now I know 0, 1, and 2 is true, so 3's true. So now I know 0, 1, 2, and 3 are true, so 4 is true. Right? That's strong induction. All right, so what are we doing here? Our statement S of I is that our recursive program that we have written works for every input of size I. All right? That's what we want to prove. And if we can prove that S of I is true for all I, right, then we know that it works for every input. Right? So how do we do it? Well, we first consider the base cases, and we prove that for sufficiently small inputs it works. Right? And then I consider an arbitrary, now I want to prove S of I is true. Right? What's the statement of S of I? It's a statement that for every input of size I, the program works. Right? How do I prove that? Okay? I want to prove for all inputs of size I. All right? Well, how do I prove for all? Give me an arbitrary input of size I. All right? Now I have an arbitrary input of size I, and I want to prove that it works. How do I do that? Well, I assume that it works for any input that's smaller than my input. Right? So that's the whole thing of trust your friends. You assume that your friends magically solve the problem. Well, then what does my code do? My code constructs instances which are smaller and gives it to their friends. Well, we know the code works for those inputs. Right? So my friends are in fact trustworthy. And they do in fact give me the right answers for their instances. And then what we already proved is that if the smaller instances give me the right answer, then mine will give me the right answer. Right? So we've already proved this. And from that we get it works for all inputs.
But that's all assuming, right? That's all assumption. You assume they're correct. That's why you use assumption to prove it.
Right.
But that's all from assuming.
Yes.
You don't know if it's right or wrong.
Yes. So we've done the two steps of induction. Right? Now what's left is trusting strong induction. And what does strong induction mean? As well, how do we know it's true we want to check that it's true for all integers, right? How do we know it's true for 0? Well, we prove the base case. How do we know it's true for 1? Well, we assumed it was true for 0, and if it was true for 0, it was true for 1, but it was true for 0. So it's true for 1, right? So now we've proved it's true for 0 and 1. Well, now why do we know it's true for 2? Well, we assume it's true it is true for 0 and 1, so it is true for 2. How do we prove it's true for 3? Well, it is true for 0, 1, and 2, so it is true for 3. Does that make sense?
How is that different from the normal induction? We know n, and then we know n plus 1 is
right.
true.
So the difference is that you only, if we remove this bit, it's normal induction. You assume the previous to get this. Strong induction, you get assume more. And why do we need to assume more? As well, because if I have an input of size I, the input I give my friend might not be of size I minus 1, right? It might be of size I divided by 2. It might be, who knows, it might be really much smaller.
So what's the advantage of having just regular induction versus strong induction? Why do they even have it?
Why do they have regular induction?
Yeah.
I don't know. Probably because for most problems you do in high school, all you need is regular induction, so why cover the harder one? And then if you're a really Ivy Tower logician, then there are systems of mathematics where you assume regular induction is true, but you don't assume strong induction is true, and you get different proof systems. I don't know. Let me tell you right now, this is the only time you're going to see strong induction in this course. Right? I'm never going to, we're done it. This is it, right? What I want you to do is these things, and then be happy that you're done. All right? And I have on exams at times, sometimes says, explain to me the connection between strong induction and recursion, and you have to kind of explain this page. Right? Another step you have to do is you have to define the recurrence relation and look at the running time. Right? You're going to have to do this for every recursive program we ever look at. I'm going to want to know its running time. Just like, count on Monday, I'm going to give you a problem and you're going to have to know the running time. Right? As
function of the input?
As a function of the input. All right, so we already did the case where I have A friends, right? And each friend is given an input that's B smaller, and I personally do F of n work, right? We'll do this case when we do Tower of Hanoi. All right, so that's what we've done. Everybody kind of get what are the pros and cons? The pros is you only worry about one step. It's an abstraction, which you don't have to worry about so much. You can make sure your program works. What are the disadvantages? Is students, unless I yell at you, and I've been yelling at you, so you probably won't resist it. But in the past, I would tell people to do this, and they wouldn't do it, right? So the reason I yell at people is not so you drop the course. It's so that you do what I tell you to do. All right, so do not resist this, right? And also, students tend to expect too much from their friends, right? You know, make sure what you give your friend is a sub-instance that meets the precondition, right? Make sure that, or else you will fail, right? It's very, I try to be very clear here. And don't expect too much from your boss. You know nothing about your boss's input. You know nothing about anything outside of your little world. Right? Everybody good with this? All right. So here is a very innocent little piece of code. All right. What does it do? If n is 0, it stops. If n is 1, it prints x. If n is 2, it prints y. Otherwise, it prints a, recurses on n minus 1, prints b, recurses on n minus 2, prints c. Right? You don't get much easier. Now, I think you should all sort of try to explain to me what this program does by tracing it out. Right? I dare you. All right, so it's easier to do it one step at a time. All right, so what does it do on 1? It outputs x. What does it do on 2? It outputs y. So don't worry about that anymore, right? Assume that works and just be a believer. All right? So what does it do on 3? Well, we know it outputs a, b, and c, right? Here it recurses on 3 minus 1, which is 2. So what does it put in here?
Y.
And what does it put in here? An x, right? Good. So that's what it does on 3. No longer worry about it. Be a believer, right? What does it do on 4? Well, it does a, b, and c, but what does it put in here? Puts a nat. What does it put in here? Puts a y, right? That's what it does on 4. What does it do on 5? It puts that in there and that in there, right? And so on. What does it do on 10? All right, so let's think about the running time. On n equals 1, it outputs 1. Let's say measured time is how many characters get outputted, right? On time 1, it outputs 1. On time n, it recurses twice and outputs 3 characters. All right? Now, solving this recurrence might be a little bit of a pain in the butt. First off, is this recurrence relation defined?
What do you mean?
Just what I said. Do you know what T of 10 is?
No.
Why not?
You need more initial conditions.
You need more initial conditions, exactly. It's not defined for 2. Right? All right. So let's just kind of wave our hands around, and ignore the fact that these are different, and put a 2 there. In fact, we probably even ignored the 3, and we'll come out to, we'll do this in more detail when we do Towers in Hanoi. But the bottom line is that this is going to be exponential size. All right? I have 2 friends, they have 2 friends, they have 2 friends, they have 2 friends. It grows fast. Right? Everybody, any questions? Oh, Tower of Hanoi. Hey, here it is. All right. Towers of Hanoi is one of my, I like Towers of Hanoi, and it comes up in life, and I would recommend that you understand this. So if you're asleep, wake up right now. All right? Understand Towers of Hanoi. All right, so what's my goal? I have 3 pegs. Each peg has a stack of discs. The discs are of different sizes. One of the rules is you never can put a disc on top of a disc that's smaller, right? Another rule is you cannot put a disc over on the chair, right? Another rule is you can only pick up 1 disc at a time, right? Has everybody played this game? Anybody never seen this? You've never seen it? Fair enough. I grew up with a father who's a mathematician, so this was just the kind of thing we did for our amusement. All right, so my goal is to move this tower from there to there, right? So it's kind of hard to know where to start. I start, in some ways it's obvious how to start. I got to pick up the first piece and I put it here and here, right? But how the hell do I know whether to put it here and here? And then what do I do, right? It gets confusing. Right, so it's daunting. Where do I start? Well, let's not start at the beginning. Let's start in the middle. All right? In the middle, I'm lazy. I am, So I think, what do I want to do? I'm going to get my friends to do a lot of work, but what personally do I want to do? I don't want to worry about little piddly sort of pieces at the top. My job will be to move the biggest piece. So at some point, if I'm going to move this tower from here to here, at some point, this big piece needs to be moved, right? And where do we want to put it? Well, we want to put it over here, right? And when I'm moving this piece from here to here, nothing can be on top of it, right? And nothing can be over here, and nothing can be on the chair, and nothing can be out of order. So where are they? They're here, in order. Right? Everybody agree that to get from here to here, at some point, the world has to look like this. Right? So that will be my job. Now, that's what I just said. They need to be over there. So how do we get these from here to here? We ask our friend to do it. So we have to make sure of 2 things. What are the 2 things we have to make sure of?
Smaller.
Smaller?
Same problem.
Same problem, right? So, if we have to make sure our precondition is well enough defined to say, well, the disks are various places, and we need to move some number of them from someplace to someplace, right? And if we make the precondition general enough like that, then then this meets the precondition. And then it's smaller. Why is it smaller? Because there's 1 disk less, right? So we just get our friend to do it. And how do we move these down here? We get another friend to do it. Everybody got it? That's the entire algorithm. And we've kind of, not only did I tell you how to do it, but I sort of proved to you at the same time that there's no other way to do it. Right? This is it. And what do I move the disk. All right, so here's the code. What's the input? You have an in, a source, and a destination, and a spare. Those are the names of the 3 towers, right? And the precondition is that the in smallest disks are on the source, right? Now there may be lots of other disks, right? All the bigger disks could be wherever you want them to be, right? I don't care. But the in smallest disks are on top of the source pole, and I don't have to worry about the bigger disks because they're all bigger, and I'm going to leave them where they are. right? But the n smallest ones, I'm going to move over to the destination tower. Everybody good with that? Now, if n is 1, I only have to move the little disk, right? And how do I do it? I just do it. I move it from the source disk to the destination disk. Okay, everybody good? And if there are more than n of them, you know, then, right, I guess the assumption here n's not -5, you know, but if there are more than, then I get my friend to move all but one of them from the source to the spare, using the destination as his spare, right? Because this is source, destination, spare. I move from the source to the spare. And then I move the nth disk from the source to the destination. And then I get my friend to move all but that big one from the spare where they are over to the destination. And we're done. All right, everybody good? So one way of thinking about this is that you're working at the Tower Hanoi company, right? And you could start, you know, they don't hire you, they hire you at an entry level. And at the entry level, your job is to move disks of one disk, right? And you do that for a while until you're really good at it, right? You're really good at moving the one disk. And then they promote you. And now they promote you to being a person who moves 2 disks. But they hire somebody under you who knows how to move 1 disk. And you do that for a while until they promote you to 3 disks and 4 disks, right? You always have people under you. Now, the way I like to think about life is that I don't have to start at the bottom. You know, I get transferred right in and I'm the president. Right? So I think I got to move n disks and I have somebody under me who can move n-1 disks. Now let's think about the running time of this algorithm. You know, the time is how many disks do you actually move? Well, if n is 1, I move 1 disk. If n is an arbitrary number, right? I have 2 friends. Each friend is asked to move n-1 disks, right? So the amount of time it takes him and his friends is t of n-1. Everybody, right? And I personally move 1 disk. Everybody got this recurrence relation? Could everybody write the recurrence relation down? Guaranteed you will have to. Right? Given this code, you should be able to write this down. Any questions about it? This line down here?
Yes.
Yeah, so what is T of n? T of n is how many disks do me and all of my friends have to touch in order for a tower of size n to be moved, right? So we look at the code. If t is 1, then I move a disk. 1 disk, it's 1. Otherwise, what do I do? Is I ask my friend to move n-1 disks. How long does it take him and all of his friends? Well, by definition, it takes him t of n-1 time. Right? Then I move a disk. That's this one here. And then another friend moves n-1 disk. How much time does it take him and all his friends? That takes him another t of n-1. Does that make sense? You just sort of go through the code and you write it down. So let's not worry about the 1, right? Because it just makes our life a little uglier. And in fact, by deleting the 1, anybody idea what we're counting if we delete the 1? We're counting now the number of times that the top disk moves, right? You think about it, if we count the number of times the top disk moves, then t of 1 is 1 still, right? Because I have to move the top disk. And t of n, well, it's the same as it was before, except we don't count this because it's not the top disk. Right? So this is the number of times we move the top disk. Well, we expand, right? What's t of n-1? It's 2 times t of n-2. Right? Everybody got that? And what's that? Well, that's 2 times 2. That's 4 of t of n minus 2. Now, what's t of n minus 2? It's 2 times t of n minus 3. Right? And 4 times 2 is 8. 8 times t of n minus 3. Right? You'll note this is, what's 8? 8's 2 to the 3. Right? So in general, we get 2 to the I times t of n minus I. Alright, people following this? And now you set I to be n, and you get 2 to the n times t of 0. Well, I don't know, maybe we're off by 1. Right? Alright, so now the bottom, we had that chart of solving recurrence relations. Now we're going to solve the ones where I have A friends, and each of them is given an input of size n minus b, right? Before it was n divided by b. And I still do f of n work. Everybody got this? And we want to figure out how much the total amount of work. Well, what is the size of my input? Is n. What's the size of my friend's input? Oh, I guess n minus b. And then
2.
n minus 2b. Right? n minus b minus b. At the ith level is n minus ib. Right? How many levels are there? Right? We go down until we have an input of size 0. There we have n minus hb is 0. So you solve for h. H is n divided by b. Excellent, thanks. We'll just finish this chart and then I'll run to this other class. So that's now, remember the number of levels before was log n base b. Right? We divided by b each time. Now the number of levels is n divided by b. Right? Which is bigger? Right? Log b is pretty small. N over b is pretty big. Right? So if they have inputs of this size, then this is how much work they do. Right? Personally. How many stack frames? It's the same as it was before. I have 1, then A friends, and A friends, and A friends. It goes up. So there are 2 to the A friends at the ith level. Right? And so the ith level is A to the I times this. Right? And at the bottom, right, it's A to the n over b. Right? This is exponential. Right? And that's the number of base cases, right? We have an exponential number of base cases. You know, and if b was 1, which it was for Tower of Hanoi, right? Then this is, and we have 2 friends, and this is 2 to the n, right? Oh, just as an extra warm-up, what happens if I only have 1 friend? What changes if I have 1 friend? What changes is it's 1 friend all the way down. I have 1 friend, I have 1 friend, right? So now it becomes the sum of these, right? Which generally will be, will probably be n squared. But we don't have time for this right now because we're leaving. All right, see y'all Friday.